I would be remiss if I was teaching you about universal gravitation and not giving you some understanding of the tides. You're all familiar with the tides, the movement of the water, bulging of the water on Earth, where the water rises and lowers in different areas at different times on Earth. So what force is responsible for these things called the tides? I'll bet you could guess. It starts with a G. Okay, it's gravity. And its gravitational tug is responsible for the tides. Although I say that a little loosely at this point. It's close enough for my purposes at the moment. But then we realize that the sun and the moon both pull on the Earth appreciably. And so let's use a little logic. If gravity is the force responsible for the tides, are greater tides produced by the sun or the moon? Logic would say, I believe, I would guess, that it'd be the one with the greatest gravitational pull would have the greatest effect on the tides. Does that make sense? Well, let's discover which one has the greatest gravitational pull. We recognize, of course, that the Earth orbits the sun. The sun is kind of controlling the Earth in that sense. But the moon orbits the Earth. Is that enough to tell you which one pulls harder? Well, realize that gravity is an inverse square law. The sun is a lot more massive, of course, but it's also 400 times further away than the moon is. So the moon is 400 times closer. And because of the inverse square law, 400 squared is 160,000. So just simply based on the difference in distances between the sun and the moon from the Earth, the moon has an advantage of a factor of 160,000 based on its proximity compared to the Earth. So it may not be so obvious. But you already have some background information that probably informs you what the tides are caused by. Caused by being in quotes right now, even though you don't see them. Is it the sun or the Earth that has the greatest effect? Well, let's go ahead and get down to the particulars. There's the formulas for the gravitational force of the sun and the Earth. Okay, so the subscript, sun, Earth, distance, orbital distance between the sun and the Earth, actually just separation distance. The moon, we have moon and Earth and distance between the moon and Earth squared. So all that compares the sun and the moon's pull on the Earth. So there it is reduced down, and there's the numbers. You'll have to trust the numbers. You'll see that the distance to the sun, distance to the moon are quite a bit different. So are the masses of the two objects. So they're in opposite directions. So let's see what we get. Here's what the calculator tells me, and this ratio is approximately 180. Uh-oh. What that says is that the force of the sun compared to the moon is 180, so it's the sun that's 180 times the gravitational pull of the moon. So even though the moon is 400 times closer, so it's got this force bias of a factor of 160,000 times greater than the sun. The sun's mass is so much larger than the moon's mass that it still has way more gravitational pull on the Earth than the moon. So now you might be confused and being concerned. You've always been told it's the moon that makes the biggest tides, and now, I guess it's the sun, huh? It's 180 times greater pull. Well, don't despair too much. In fact, it is the moon that produces the greatest tidal effect. Okay, you can breathe a sigh of relief, but you're confused. But you won't be in a minute, because the confusion will be alleviated when you understand the concept of differential tug. It's the differential gravitational force of these objects on the Earth that really produce the effect we call the tides. Let me illustrate with a point mass producing a G field. Here it is, mass M. And here comes a cellular entity. Yes, it is extremely yucky. It is squishy, gooey stuff. So if you grab this thing with your fingers and squeeze it, it'll distort all over the place. So that's why, one reason why I like hard science is because it's not so squishy. In any case, let me make this simple, really simple here. It's a distance d from the point mass to the near side of the cell. And then there's another distance d of extension across there. So to the far side, g far, or Jafar, it's 2d to Jafar. Now g is proportional to 1 over r squared. And so because of that inverse square law, if we do the strength of the g field from m on the near side and compare the strength of the g field on the far side, which is twice as far away, we get 1 over d squared over 1 over 2d squared. Everything else, the masses and the universal gravitational constant, divide out, so I just eliminated those. And this is simply 4, which you can easily conclude. Which means that the tug on the near side, because it's directly proportional to the g field, is 4 times greater than the far side. In other words, it pulls harder on this side than this side. What happens to an object, assuming it doesn't come apart, if you pull harder on one side than the other side, and it's squishy? In other words, it can be deformed. Hint, hint. In fact, that's exactly what happens. It deforms. So you start with this squishy, gooey cell, and you end up with? Yes, this squishy, slimy, slithering, deformable, and now it is deformed, cell that's been stretched out into this new configuration. So we've stretched it out, and that effect is really what the tides are doing, pulling harder on one side than the other side, resulting in a deformation of the object. In the case of Earth, it pulls the water to one side, stretches it all out because it's easy to move the water, so to speak, and so you get bulges. So let's look at that a little more carefully. Okay, let's look at how this works out for the sun and the moon. Let's look at the differential tug from the sun. So here's our beautiful sun and Earth, and there's the moon. All right. The Earth diameter, 13,000 kilometers. The sun pulls on the Earth. Now we know it's pretty hard that it pulls on it. So think of this as a vector. It's just some relative size corresponding to the tug of the sun on Earth. On the near side and on the far side. And of course, the far side is going to be less than on the near side. The moon does the same thing. We got the near side tug and the far side tug. And the far side, is less than on the near side. Now, let's look at the sun alone. The ratio of the tug on the near to the tug on the far. This ratio, simplified down, gives us the ratio of, it's an inverse square law, so you flip around and it's far over near quantity squared for the radii, or the distances. Now to get a handle on this, the near side I'm just going to call 1.496 times 10 to the 11 meters. I need all these decimals in here because the 13,000 kilometers additional shows up right here at this point in the decimal places. So the far side is a little bit more, and we need to keep all those decimals in to see what's going on. This gives us 1.00017. Basically, that's 17%, I'm sorry, 0.017% difference in force between the near and far side. So if it was exactly equal to the 1 to 1, there'd be 0% difference. So basically, you take this number, you subtract off 1, move the decimal over 2. So we got 17 1/1000ths of 1% difference between the two tugs. Okay, that's not very much difference, is there? Of course, realize that this force, that this whole thing, is with the condition that the sun is still pulling 180 times more than the moon is. So we got to consider that. We'll take that into consideration properly. But let's do the same thing with the moon. The ratios of the tugs, near and far. gives the r far over r near squared. There's the numbers. Now look at in the decimal places, it shows up a lot sooner. There it is, the first and second decimal places. This is 1.0702, which really is a 7% difference between the near and far side. So 7% difference compared to 0.017%, because the relative amount of additional distance to the far side is much bigger for the moon because it's so much closer to begin with. So that proportional effect is much greater. But because the sun pulls 180 times as hard as the moon, to compare this fairly, we need to take the differential tug of the moon compared to the sun, which is really the thing that matters, the differential tug. We compare those. I'm going to do it by comparing the percents and then factoring this up 180 times because of the much greater tug of the sun. So it's 7% over 17/1000%, but this times 180. This gives us 2.3, which really says still, even though the sun is pulling so much harder, that percent difference is so much less that the moon still has an advantage, 2.3 times the effect that the sun does. So there you go, folks. The moon is the primary contributor to the tides, but the sun is not negligible by any means because it's 1 compared to 2.3. Okay. The result of all this, we just take the Earth and the moon in isolation. The sun isn't in here now. We get a stretching of the Earth. This is actually land tides. It's not very much, and you don't even notice it, but the land is stretched apart. But the part we do notice is the water tides, because the water moves around and we see that happening. We have smaller bulges on the other side. You might think about why that is. Why are there smaller bulges on the other side? You can't say the sun, because the sun isn't even in this picture right now. It's just the moon and Earth. So I'll explain that a little bit more in part 2 of this, of the tide sequence here. But we got larger bulges on the front side. So for the time being, you can understand that it's pulling harder on this side than this side. So you get these bulges both in land and water. And that in basic is what produces the tides, this differential pull. And let's look at that in a little bit more detail in part 2.